In this video, I'm going to discuss the basic formula for MCTC, that is movement to change the trim by 1 centimeter. So this is a vessel, and this one is the center of gravity of the ship. Well, center of gravity is the point where total weight of the ship can be assumed to be acting vertically downward. Let's say the weight of the ship is capital W, and that will be equal to m into g, where m is the mass of the ship and g is the acceleration due to gravity, while the average value of g is 9.8 meter per second square. Now let us assume that this is the water line. So this means that this is my underwater area or underwater volume. This is my underwater portion. The center of buoyancy is the geometrical center of this underwater portion. The force of buoyancy acts vertically upward from a center of buoyancy. Well, it is acting like this. Now assume that we have this W ton weight here, and we shift this weight from forward to aft like this. Now this small w, this weight is shifted from forward to aft like this. So if this weight is shifted from forward to aft, it will also shift or change the position of center of gravity, and center of gravity will shift from G to G1 in this direction. Now this force, the weight force, will act from G1 instead of acting from G, and this will trim the ship like this. Well, since G is shifted from G to G1, the center of buoyancy will also shift from B to B1. It makes sense also because the underwater volume is increased on this side. Now this is the underwater volume. Earlier the underwater volume was only this one. Now it is increased, so that means B will also shift from B to B1. And this way the force of buoyancy, instead of from B, it will also move and it will act vertically upward from B. Well, this weight is shifted from forward to aft with the distance d. So we can say the shift in the center of gravity of the ship is a GG1, and that is in this direction, G to G1 in this direction, and it is going to be small w into d divided by capital W, where small w is this weight and d is the distance shifted. Well, from this place to this place, distance is shifted, and capital W is the displacement of the ship. Well, we also note something very interesting here, that tan theta is equal to GG1 by GML, and this is if we consider this triangle. So let me mark this triangle. G to G1 is going to be like this, and this is angle 90 degree. And this triangle is, let me just mark here, G to G1 like this, and this one. So this is the triangle, and in this triangle we have the relationship GG1 divided by GML, and this is ML is nothing but longitudinal meta center. Well, this ML is nothing but the intersection of initial line of buoyancy. This is initial force of buoyancy, and this is after shifting B to B1. This is the next or successive force of buoyancy. This is successive force of buoyancy. So the intersection of these in a longitudinal direction is longitudinal matter center. So we have this relationship tan theta is equal to GG1 by GML. Now we have one more interesting thing, and if we consider this triangle, let me highlight this. This will be much better. I'll use this green color. If we have this triangle here, this one, this triangle. So in this triangle we have this relationship that tan theta is equal to trim by LBP. Well, this length is LBP, length between perpendicular. So we have one reference line here which is forward perpendicular. We have another reference line here which is aft perpendicular. So the distance between forward perpendicular and aft perpendicular is length between perpendicular, and this is trim. Let me again define the trim. Trim is the difference between forward draft and aft draft. So this is the forward draft. Forward draft is a vertical distance from waterline to the keel or vice versa, and aft draft is this one. This one is my aft draft. So the difference between forward draft, and this is also forward draft, this distance. So the difference between forward and aft draft is going to be this one. This is trim. Now let's work on this. That GG1 is W into D by capital W, and W into D is trimming moment. Well, the trimming moment is defined as the weight W and the distance shifted. So this W was shifted from forward to aft like this with the distance D. So we have this trimming moment. Trimming moment W into D divided by capital W. Also, we have very interesting relationship between TM and MCTC. Well, the trim cost is the trimming moment divided by moment to change the trim by 1 centimeter. Say for example, if MCTC is 200 ton meter, that means this is the moment required to change the trim by 1 centimeter. So if I have 2000 ton meter trimming moment, how much trim change will I have? Well, obviously it is going to be 10 centimeter, which simply mean that this 10 centimeter I will get by TM dividing, this is TM, 2000 dividing by MCTC. So we have this relationship where TC trim cost is nothing but trimming moment divided by MCTC. So if TC is 1 centimeter, that means this TC is 1 centimeter, we have trimming moment is equal to MCTC. Well, we just assume that TC is 1 centimeter. Now, suppose the initially the initial trim was 0. The ship was at even keel, and the final trim is say T. So the trim cost will be equal to trim. Let's go back here. So initial trim was 0. Well, the ship was at even keel. The ship at the line, this was the water line. Initially the water line was like this. So the forward draft and aft draft was 0. However, when the ship has trim, the forward draft is only this one and aft draft is this one. The difference is the T. So trim cost is equal to trim. Well, so trim cost is equal to trim. Well, we have one more interesting relationship, that tan theta is equal to trim by LBP, and the trim is 1 centimeter, and we use the unit in meter. So the 1 centimeter is equal to 1 by 100 meter. I can write like this also. Tan theta is equal to 1 by 100 into LBP, that is length between perpendicular. So 1 centimeter I have written as 1 by 100. This quantity I have just is 1 centimeter. Let me again mark just to emphasize this. Now if we come back to this formula, that tan theta is equal to GG1 by GML. So the GG1, we can write this information that GG1 is W into D by capital W, or trimming moment divided by W. So I write GG1 as trimming moment divided by capital W into GML. And just now we have worked out that if the trim is 1 centimeter, trimming moment is equal to MCTC. So instead of trimming moment, I write MCTC divided by W into GML. So we have two relationship here. By the way, this angle is theta and this angle is also theta. So we have two triangles here, say X, Y, Z. And there is another triangle is also there, which is G1 and GML, this triangle. And both these triangles are similar triangle and their properties can be verified by simple geometry. So here the tan theta is equal to trim by LBP, where I am using this triangle XYZ, and tan theta is equal to GG1 by GML, where I am using this triangle. Now this 1 by 100 LBP, that is tan theta, trim by LBP, which is 1 by 100 LBP, is equal to GG1 by GML, which is MCTC by W into GML. Well, this has come from this formula, that tan theta is equal to trimming moment divided by W into GML, or TM, trimming moment, is equal to MCTC. So this has come from this formula here. So this tan theta is equal to this tan theta, this tan theta is equal to this tan theta. All I need to do is now just equate, and I get this relationship where MCTC is W into GML divided by 100 into LBP, and that's a very useful formula.